I remember when I was a student and my professor would make a promise, and I would always remember those promises. And so as a professor, I'm always very careful to make sure that I keep my promises. I think the only promise that you have pending from me right now is to explain essentially what's up with NAND and NOR gates. Why do we care about NAND and NOR gates? Why don't you just keep those as just an AND gate followed by an inverter? And the answer is that it turns out that NAND and NOR gates are the only two universal gates. In other words, you could build any digital logic device just from an infinite supply of NAND gates or from an infinite supply of NOR gates. You don't even need both. You just need one or the other. Now, if you don't have NAND gates or NOR gates, then you need at least an AND and an inverter, or an OR and an inverter, or the best, sort of the easiest case, is if you have ANDs, ORs, and inverters. That's the ideal toolkit, is ANDs, ORs, and inverters. But we're going to talk more about that when we talk about digital logic design. For today, we're really just talking about universal gates. So it turns out that one of the reasons why this is in today's lesson is because you could simplify the circuit significantly by reducing the number of different types of gates. Because if you buy an AND gate, it actually comes on a chip that has 4 AND gates. If you buy an OR gate, it comes on a chip that has 4 OR gates. An inverter comes on a chip that has 6 inverters. NAND and NOR each come 4 to a chip as well. So if I give you a circuit to build and you built it with 1 AND gate, 1 OR gate, and 1 inverter, doesn't sound very complicated, but you're going to need 3 different chips. But if you could actually build that same circuit using just NAND gates, using just 3 or 4 NAND gates, then you can do it with just a single chip. So universal gates can really reduce your chip count, and that can make a big difference in the final solution that you're looking for. So I'm going to focus on NAND gates. I have to tell you that exactly the same analysis would work for NOR gates, and I know that you're smart enough to be able to figure out that same analysis. So I'm just going to focus your attention on NAND gates, and then later on, if you want to, you can go back and verify the same thing will work for NOR gates. To be able to convert a NAND gate into an inverter, all you have to do is tie both inputs to the same signal. So here you can see I have both inputs of the NAND gate tied to A, and then the output will be equal to A bar. Well, we know that just on the inside of the bubble here, that'll be A and A. A and A is just 1, or I'm saying A and A is just A. So when we invert it, that's when we get A bar. So that's the first piece of the puzzle, is to know that you can build an inverter just by tying the 2 inputs of a NAND gate together. Then, if you just do a NAND, so if I have A NAND B, and then if I put my newfound inverter after that, then I end up with A and B. Because this entire structure here, the second half, cancels out this bubble, and then I'm left with just an AND function. So NAND gates can implement an inverter. NAND gates can implement an AND gate. Can NAND gates implement an OR gate? Well, yes. It's a little bit harder, but we're going to use Demorgan's theorem to see that if you put an inverter on each of the 2 inputs, so here I'm inverting A to get A bar, I'm inverting B to get B bar, and then if I NAND A bar NAND B, so you can see here I get not A and not B with a bar across the entire thing. If I use Demorgan's theorem, I can break the big bar into 2 shorter bars, convert the AND function into an OR function, and then the 2 double bars, those each cancel each other out. And so I'm left with A or B. So if you want an inverter, tie the 2 inputs together. If you want just an AND gate, put a NAND gate followed by an inverter. And if you want an OR gate, put a NAND gate preceded by an inverter on each of the 2 inputs. Now again, you can do the same analysis using NOR gates, but we're going to focus on NAND gates in this class. You'll have plenty of time to look at universal gates again next year. But for right now, you've got enough information to solve the universal gates example problem, which is going to ask you to just implement a given function using strictly NAND gates.